Take a look at this sentence. The animal didn't cross the road because it was too tired. As a human, you instantly know what the word it refers to. But from a strict grammar perspective, identifying it is a bit of a puzzle. Your brain solves this using the words around it. You know that animals get tired, but roads do not, so your mind naturally draws an invisible line connecting it directly back to the animal. For decades, early artificial intelligence programs struggled with this. They lacked the ability to look at a sentence and make that same connection. Understanding language is more than just knowing the definitions of individual words. It requires mapping out exactly how every word in a sequence relates to the others. Before 2017, the standard way to teach a computer to read was to feed it text in a straight line. Imagine reading a book through a tiny peephole, where you can only see one word at a time, moving from left to right. By the time the computer reached the word it at the end of the sentence, the word animal from the very beginning had often already faded from its memory. This step-by-step process made training very slow. Because the computer had to finish one word before it could start the next, it couldn't take advantage of the way modern computers are designed to handle many tasks at once. Treating language like a linear assembly line made it difficult for AI to grasp the full, interconnected meaning of a paragraph. Researchers realized that for AI to truly understand context, they needed to move beyond reading in a straight line. They created the transformer, which looks at the entire sentence all at once. This allows self-attention. Each word reaches out with a mathematical thread to every other word. The model scores these relationships, forming a much stronger connection between it and animal than road. By calculating these scores across the whole text simultaneously, the machine builds a context map, ensuring it never forgets a word it just read. However, language has many layers. One pass over a sentence might catch the grammar, but it might miss the timing of events or the relationship between different people. To solve this, the transformer uses multi-head attention, creating 8 different attention threads that run simultaneously. Each head focuses on a different task, like grammar, pronouns, or overall intent. Finally, they merge their findings back together into a single, detailed web of interconnected information. Tracking several different types of relationships at once allows the model to handle the complex nuances of the way we speak. Looking at all the words at the same time didn't just help with accuracy, it made the systems much faster to train. Instead of waiting for one word to finish before moving to the next, the transformer uses modern computer chips to perform thousands of calculations simultaneously. This speed allowed researchers to feed the model billions of words. It moved from learning from single books to ingesting entire libraries and huge portions of the internet. Removing the step-by-step limitation is what allowed AI to grow from small programs into the massive systems we see today. The structure introduced in that 2017 research paper is the foundation for almost every modern AI tool, from GPT to Claude and Gemini. When you ask a chatbot a question, you are seeing billions of these attention threads firing at once, instantly calculating how every word in its vast memory relates to your request. These systems aren't just memorizing definitions, they are using math to navigate the relationships between ideas. It turns out that to build a machine that truly understands us, attention is all you need. In 2017, a team of researchers designed an architecture to solve machine translation. The objective was to accurately convert text from one language to another, not to build generalized artificial intelligence. Before transformers, recurrent neural networks process data sequentially, reading sentences strictly in order, one token at a time. This linear dependency prevented parallel computing, degrading relationships in long sequences. The transformer replaced this sequential loop with simultaneous mathematical interactions, allowing all tokens to communicate instantly. To understand the large language models operating today, we have to look inside the original architecture and construct the mathematics of a transformer layer step by step. Shifting from a step-by-step loop to a highly parallel matrix of operations allowed models to fully utilize graphical processing units. This alignment between mathematical theory and raw hardware capabilities is what made massive computational scaling possible. The first physical step requires converting raw text characters into discrete numerical token IDs. Computers do not understand words, so each distinct linguistic fragment is assigned an integer value. This visual represents the embedding layer. Raw token IDs are projected into dense, multi-dimensional feature vectors, mapping every token across hundreds of hidden dimensions. Words that appear in similar contexts occupy similar coordinates in this vector space. Verbs cluster near verbs, pronouns near pronouns. Because the transformer views all tokens simultaneously, it lacks an inherent understanding of word order. The sentence structure is flat. Identical words appear mathematically identical to the model, regardless of where they sit in a paragraph. To solve this, the model uses positional encodings. It overlays a mathematical wave function onto the embeddings, adding numerical values representing relative distances. This wave pattern ensures identical words receive unique mathematical signatures based on their row position. Through the combination of embeddings and positional encodings, raw text mapping is complete. The words exist within a continuous, ordered mathematical space, prepared for active computation. Self-attention relies on 3 distinct representations. The network multiplies every token vector against 3 separate learned weight matrices, projecting them into a query, a key, and a value. The query represents what the specific token is looking for. The key represents what the token contains. The value holds the underlying semantic data that will be passed forward. This diagram illustrates the core operation, a dot product multiplication. A single token's query multiplies against every other token's key in the entire sequence, generating a row of attention scores. Higher dot product scores indicate a stronger contextual relationship. The mathematics dictate exactly which other words in the sentence are relevant. The single row of scores expands downward into a full n by n heat map grid, generating a complete map of interactions. The attention matrix serves as a complete numerical record of token relationships, defining the exact weight every word exerts on every other word in the sequence. Language mechanics are complex. Tracking the grammar, the pronouns, and the verbs simultaneously requires more relational data than a single matrix can provide. The token dimensions divide, running the query, key, value dot product across parallel layers. One head maps grammar, another maps meaning. These independent heads concatenate back into a single matrix, combining multi-layered scores with semantic data. The concatenated data passes through a feed-forward network. This operates independently on every single token, allowing the model to learn abstract features without blending the sequence data further. To stabilize the vast numerical outputs of these operations, the architecture utilizes residual connections and layer normalization. These steps prevent data loss and stop values from oscillating out of proportion as they move deeper into the network. At the end of a single encoder block, the raw input sequence has transformed. It is fully enriched with calculated grammatical dependencies and relational understanding. The 2017 architecture relied on an encoder to process input text and a decoder to generate the translated output. Modern generative models strip out the encoder entirely. Decoder-only structures proved more efficient for autoregressive generation. Their design is focused entirely on calculating the probability of the single next token in a sequence. This visual shows masked self-attention. During training, the upper right diagonal of the attention matrix is blocked. A token cannot query the keys of tokens that appear later in the sentence, preventing the model from looking ahead. The decoder output vectors route through a linear layer and into a softmax function. Softmax converts the final attention scores into a clean probability distribution across the entire vocabulary. The token possessing the highest probability wins. It is selected, outputted, and then physically appended to the end of the original input sequence. The process starts over. Modern generative models simply execute this masked single-token prediction loop repeatedly to build coherent paragraphs. The self-attention mechanism carries a significant computational cost. Comparing every token against every other token results in quadratic complexity, mathematically defined as O of n squared. This chart tracks the cost of quadratic scaling. If you double the number of tokens in the sequence, the required mathematical comparisons quadruple. For long context models, memory consumption can explode. Operating on thousands of tokens simultaneously under naive calculation methods would eventually exceed the hardware's capacity. Real-time text generation with large context windows is only possible through specific engineering optimizations. To solve this bottleneck during inference, engineers deploy the KV cache. This diagram illustrates the KV cache mechanism. Previously computed key and value matrices are saved directly into memory. When predicting the next word, the model reuses the saved states, ensuring only the absolute newest token requires a full query computation. Bypassing redundant math prevents the context window from exhausting the graphics processor. Optimizations like the KV cache and flash attention translate the theoretical framework into a viable software product. Modern systems deploy hundreds of billions of parameters. However, the fundamental dot products and matrix operations inside the layers remain the same as those described in the 2017 paper. Researchers identified clear scaling laws. By systematically increasing the volume of training data, the parameter count, and the compute power, model performance improves on a predictable, continuous curve. As models reach massive scale, researchers observe skills like coding, logical reasoning, and complex planning appearing spontaneously, despite these tasks never being explicitly programmed into the training objective. This phenomenon, emergence, suggests that optimizing next token prediction across trillions of words forces the model to map the underlying logic of the language data. The result is a system that develops generalized intelligence from the same deterministic matrix math used in the original 2017 research, achieved by increasing the raw scale of the network. A raw pre-trained model merely predicts text. It calculates the most statistically likely continuation, which often produces outputs that are erratic, unhelpful, or factually incorrect. The final stage of development applies instruction tuning and reinforcement learning from human feedback. Human operators rank the raw outputs. The model updates its weights to penalize poor responses and reward structured, helpful answers. This alignment forces the mathematical engine to act as a conversational agent. The end result of this extensive pipeline is a clean, accessible interface. It requires no knowledge of matrices or parameters to operate. Every response generated on that screen is the product of continuous, simultaneous cascades of query, key, and value matrices. Discarding the sequential loop solved the problem of computational context, establishing the mathematical baseline that governs modern artificial intelligence.